So today it's my pleasure to introduce Claudio Ricci. So Claudio did his PhD at the University of Geneva, and then he became a GSPS fellow at the Department of Astronomy of the University of Kyoto. Then he moved to Chile and became a CONICET fellow at the Pontificia Universidad Católica at Santiago. And since 2018, he's an assistant professor at the Universidad Diego Portales in Chile, and a long-term visiting professor at the Kavli Institute for Astronomy and Astrophysics in China. And today he's going to talk about absorption and accretion properties of local active galactic nuclei. There we go.
Okay, thanks, Nicolas. And thanks for the invitation. It's really a pleasure to give this online colloquium. I hope everything will work out since we are so far away. My talk is going to be focused on the absorption and accretion properties of AGN, so creating supermassive black holes with strong emphasis of objects in the local universe. A small introduction: when we are talking about AGN, we are talking about creating supermassive black holes that can be found at the center of most massive galaxies. They typically accrete material from their surroundings, which allows them to reach very high luminosities, making them the most luminous persistent sources of radiation in the universe, with volumetric luminosities up to 10 to the 48 rays per second. In some cases, they can also develop very strong jets that are observed in the radius. And during this phase in which the supermassive black hole are basically creating material from the galaxy, they can also have a very strong impact on the galaxy. And it's widely believed that they have a key role in galaxy evolution, affecting star formation in the host galaxy. Besides having such an important role in the evolution of galaxies, they also are the strongest gravitational fields in the universe. So studying supermassive black holes, in particular in the high energy domain, it's exceptionally important since they can provide fantastic laboratories to study general relativity. And this is something that I know that the group at Cambridge has been doing very successfully. Nowadays, we think that the typical structure of an AGN can be summarized in a very simplified way by this cartoon, with a supermassive black hole at the center, which is surrounded by an accretion disk at larger scales, so typically tens to hundreds of light days. One can find a Broadman region, which is the location where broad emission lines in the optical and UV are produced. This is material that is accelerated by the gravitational field of the supermassive black hole. And on larger scales, and here we are talking about hundreds of light days to parsecs, one can find a structure that is some sort of anisotropic obscurer that is typically simplified in our imagination as a torus. So this is the location, the place where most dust and gas on hundreds of light days are found. Studying this circumnuclear gas, and in particular this torus, I'm going to call it torus, but in reality the situation is probably much more complex than the donut shaped picture that one usually sees in presentations. Studying this structure is extremely important for at least three reasons. The first one being that this is an important reservoir of the accreting material that eventually falls down the supermassive black hole. It's some sort of pantry where the supermassive black hole gets the gas and dust that eventually accretes. It can provide important insight on the feedback, because this feedback mechanism with which the supermassive black holes are believed to be talking to the galaxies during the accreting phase is going to leave a very strong imprint, first on its surrounding material and then on larger scales on the host galaxy. So studying the evolution of this circumnuclear material with AGN properties can tell us something about how feedback operates and how it affects first the nuclear material and then material located on larger scales, and namely the host galaxy. Understanding all the characteristics of the obscuring material is also very important, because many AGN, and we're going to discuss about this in this talk much more later, many AGN are believed and are seen to be obscured heavily obscured in many cases, so that in order to have a full census of accreting supermassive black holes, it's extremely important to understand the properties of these obscurer, because at the end we want to know how many AGN, how many accreting supermassive black holes there are in the universe, and in order to do so, we need to go beyond this bias caused by the presence of strong obscuration. In my talk, I'm going to focus on the properties of this circumnuclear material around accreting supermassive black holes. And in particular, I want to see how these circumnuclear materials evolves with the properties of the AGN and those of the host galaxy. Another reason why it's extremely important to study this circumnuclear gas and dust is related to the way we typically think about AGN unification. So we know that there are different classes of AGN. This is something that historically was started, the classification started being based on optical spectroscopy. So scientists in the 80s and the 90s, they were looking at optical spectra and finding that some sources showed narrow lines and some sources showed both broad and narrow optical lines. The unification model foresees that these differences can be ascribed to the orientation with respect to this anisotropic absorber, this torus, so that when one is looking pull-on to the system, is able to observe both the broad lines, which are produced by this broad line region, by this gas very close to the supermassive black hole, and also the narrow lines, which are produced much further away. On the other hand, observing AGN edge-on with respect to the torus, the broadline region is covered, so it's completely extincted by this dust, so that one is able to look only at the narrow optical lines that are produced in this region that is located at hundreds of parsecs, of kiloparsecs. Another way we can think about the typical AGN unification scheme as some sort of one-dimensional diagram, where the probability here on the left of a source of being obscured is just a function of the inclination angle. So depending on how big this torus is, one is going to observe an unobscured or unobscured source, depending on the inclination angle it's looking the system at. One way to study this circumnuclear material and the AGN in particular is to look at them in the X-ray, and X-rays are an ubiquitous property of accretion. Whenever there is an accreting source, we can see X-ray emission. This is true through a very large dynamic range of masses, starting from protoplanetary systems, so masses comparable to stellar masses, up to X-ray black hole binaries. So we are talking about masses of tens of solar masses, until intermediate and supermassive black holes, which can reach masses of 10 to the 9 or 10 to the 10 solar masses. In supermassive black holes, we know that the X-ray emission is produced by an X-ray corona. This is a source where one has very hot gas and it's located close to the supermassive black hole. And the electrons in this hot gas are basically upscattering the optical UV radiation produced by the accretion disk up into the X-ray regime. This is shown in this simplified cartoon here on the bottom left of your screen, where you have at the center the supermassive black hole, the accretion disk, the broadline region, the torus, and this X-ray corona. So all these optical UV photons produced in the disk, they hit the corona, they're upscattered to the X-ray band and give rise to a very clear distinct signatures that is a power law emission with a photon index typically between 1.8 and 2, and high energy rollover at few hundred keV, which is basically related to the temperature of the plasma that is producing the X-ray radiation, since it becomes harder and harder to produce radiation at temperatures higher than the temperature of the plasma. We know that this corona is located very close to the supermassive black hole. This is something that's been seen thanks to reverberation mapping studies done in the X-rays. Here is an example of a nice paper that was published earlier this year on Nature Astronomy, in which in particular they find that the height, the location of this corona, this source of X-ray radiation, changes changes with the accretion rate of the AGN, and it's typically within 5 to 15 RGs. X-rays are also an extremely useful tool to study fundamental characteristics of the supermassive black hole, such as its spin, and this has been routinely done now using reflection features that are produced in the innermost regions of the disk, thanks to observations of broad iron lines and to other features arising from the reprocessing of this primary X-ray radiation in the disk. But how can X-rays help us to understand more about the obscuration? Since they're produced so close to the supermassive black holes, this means that they are also able to tell us something about how much gas there is in the line of sight. Obscuration leaves a very clear imprint on the X-ray spectrum of AGN. This is shown in this video here. Depending on the line of sight, you can see, depending on how much obscuration you have on the line of sight, you can see that the X-ray spectrum changes. And in particular, when one gets to very high obscurations levels, there are very distinct signatures, in particular a strong K alpha line and an emission that is basically dampened at low energies, and it's very flat and just leaves some scattered processed emission at higher energies. So in order to understand the structure of AGN in the X-ray band using their absorption properties, what we can do is to have a large sample of objects, and then from their obscuration properties, assuming that this sample is unbiased by obscuration itself, or at least that we can recover the intrinsic properties of the sample, we can say something about the average properties of this obscuring material. But in order to do so, we need indeed to find an energy band and a sample that are as little affected by absorption as possible. And this is typically done in the hard X-ray regime. And by hard X-ray regime here, I mean everything that is above 10 keV up to several hundred keVs. Because typically in this band, one sees much less the effect of obscuration. This is shown by this plot here. Here on the y-axis, you have the fraction of escaping flux, considering a certain geometry of the absorber with the X-ray source at the center. And on the x-axis, you have the column density that basically tells you how much material you have on the line of sight. And you can see that, as shown here by this red, this black line, for the hard X-ray band, so here between 14 and 200 keV, one is able to recover most of the flux up to very high column densities. And in particular here up to 10 to the 23.5 centimeters to the -2, one can see about 90% of the primary X-ray emission. As a comparison, you can see that in the 2 to 10 keV range at lower X-ray energies, most of the emission is dampened by the strong effect of absorption. So that at the same NH of 10 to the 23.5, one is able to recover about only 25% of the flux. This means that we need to observe the sky in the hard X-ray band to have a full census of accreting supermassive black hole, and also to use their absorption properties to understand the typical structure of this obscuring material. So this nowadays can be done with two main facilities. The first one being NuSTAR, which was launched in 2012, and it's a new generation hard X-ray telescope, which allows to do imaging and spectroscopy of in the hard X-ray band, and it's been a game changer, because thanks to its sensitivity and angular resolution has allowed a large number of studies that were really impossible before its launch. The second facility, it's SWIFT-BAT. So this is an older instrument. SWIFT was launched in 2005, and its BAT detector, which operates in the 14 to 200 keV, scans the sky continuously, and it's been doing so for now 15 years. The main idea of BAT was to detect gamma ray bursts, but in doing its scan, of course, has detected a large number of AGN. So all these AGN, which are selected using the BAT survey, are not very much affected by obscuration. So this is a great sample to start studies of absorption properties of AGN. So in order to understand more about the absorption characteristics, but in reality about all the properties of this sample of AGN, with Mike Koss and Benny Trachtenbrot, we started the BAT AGN Spectroscopic Survey, which is a multi-wavelength study of all the 1,000 hard X-ray selected AGN that have been detected by SwiftBAT since its launch. This is, again, a whole-sky survey, and it's being unaffected by obscuration. It can provide us a very clear, unbiased look of the accretion properties of nearby AGN. The flux limit of BUS is not very high, so this means that we are only recovering sources in the near universe and in the nearby universe, and the typical redshift of the sample is about something like 0.03. We are talking about AGN located within a few hundred megaparsec from us. Our survey consists in several different observation campaigns that were carried out in different wavebands. In the optical, we have obtained about 700 hours on VLT and 60 observing nights on different telescopes located in Chile as well as in the US. And the main idea of the optical campaign is to recover black hole masses and to do careful optical spectroscopic analysis of all these sources. We have recently put a lot of efforts in campaigns, observational campaigns in the SI millimeter and radio, and we have obtained something like 700 hours on telescope like IRAM, ATCA, APEX, and also ALMA, JVLA. In the X-ray band, we got about 3 megaseconds, but on top of this, I must stress that there is really a lot of archival data, because those are the most famous nearby AGN, so they've been routinely observed by many satellites such as XMM. NewStar has a particular campaign that is dedicated to observe all SwiftBAT sources. So in reality, there is tens of megaseconds of X-ray data. So to summarize the main effort of BUS, we are looking at the multi-wavelength properties of about 1,000 AGN in order to have main information such as luminosities, black hole masses, Eddington ratios, and column densities, and much more. In the rest of my talk, I will mostly focus on the obscuration properties of AGN, but there is much more that we are doing, and if you're curious, I'm happy to answer any question you might have on that. So now we have a sample that is well defined. It's not very much biased by obscuration. The selection function of AGN in the hard X-ray is quite straightforward, so one can in principle also take into account the sources that are not detected because they are too obscured. And we can now try to have a look at what are the average properties of the circumnuclear material of nearby AGN. So this is done by looking at basically how many sources are obscured and what is their obscuration level. Saying that a sample is obscured at 70%, for example, means that on average, the covering factor of this obscuring material is about 70%. That is because if we assume that each observation of an AGN is just sampling a random inclination angle with respect to this absorbing structure, then we can say that on average, the fraction of sources that are obscured corresponds to the fraction of the sky of the supermassive black hole that is covered by the obscuring material. So using BUS, we found that the typical covering factor of a creating supermassive black hole is about 70%. And as shown in this plot, here you have the system, the X-ray corona together with the accretion disk, and this is not to scale simplified image of the torus, and about 30% of the sky of the AGN is covered by this denser material made of content-thick gas and dust. Therefore, from these studies, we could also conclude that most of the AGN in the local universe are obscured because 70% of them show some level of obscuration, and typically we are talking about column densities about 10 to the 22 centimeters to the -2. One thing that we really wanted to address with BUS, and from my side, this was the main motivation of starting such a multi-wavelength observational campaign, is to understand what is the reason why the fraction of sources that are obscured changes with the luminosity. And this is something that had been known for over 20, 30 years, and it's shown by this plot. On the y-axis, you have the fraction of AGN that are obscured. So this again is a proxy of the covering factor of these stars or circumnuclear dust. And on the x-axis, you have luminosity. And you can see that when one moves towards higher luminosity, the fraction of sources that are obscured decreases. And the idea here is that probably this is related to some sort of feedback that the AGN is having on its nearby environment. And the same thing is observed at higher redshift, albeit with a possibly different normalization. One possibility is that this is related to radiation pressure. However, the classical definition of super Eddington source is a source that has an Eddington ratio larger than 1. Here, the Eddington ratio is a function of the luminosity over the black hole mass. But this is true for gas that is fully ionized, because we are taking into account the cross section, the Thomson cross section, so the cross section of the interaction between photons and electrons. It might well be that actually most of the material is in the form of dust, and this is something that we see from the infrared, because we know that the nuclear there is a lot of nuclear emission in the mid-infrared from this AGN. So if the material, the obscuring material, is mostly done by dust, then the cross section that one should use is quite different, and is shown here as a sigma I. This is something that was first postulated by Andy Fabian about 15 years ago, and there are several other papers that laid the basic theoretical foundation of this idea. So if the cross-section of the system is actually much larger than the Thomson cross-section, then one can in principle be super Eddington already at much lower Eddington ratios. And in particular, one can define an effective Eddington ratio, which is given by the ratio between the Thomson cross-section and the cross-section of dust in this case, which is a function of different things, amongst which the column density and the ionization parameter. We can plot this here. So here you have on the y-axis the logarithm of the Eddington ratio as a function of the column density. And this is the effective Eddington limit calculated for typical dust. And you can see that already at the column densities of a few percent of the Eddington ratio, one can be super Eddington. And in particular, for a column density of 10 to the 22, which is what we use to separate obscured from unobscured AGN, one can be super Eddington at a few percent of the Eddington limit. This means that radiation pressure on dust could actually be what is driving this decrease of the covering factor of the supermassive black hole as a function of the luminosity. In order to study this, one needs, however, to do a different kind of analysis and to look at how the fraction of obscured sources changes with the Eddington ratio. And this is something that we did here for BUS, as shown in this plot. And you can see that up to a column Eddington ratio of about a few percent of the Eddington limit, of the classical Eddington limit, one sees about 70 to 80% of the sources as obscured. Above this value, there is a very sharp drop, and then most of the sky of the AGN is actually devoid of obscuration, so that most sources are observed as unobscured. And the interesting thing is that this decline corresponds exactly to the expected Eddington limit for dusty gas, with a column density of 10 to the 22, which again is the value we use to separate obscured to unobscured sources. This is basically telling us that radiation pressure is what shapes the closed environment of a accreting supermassive black hole, so that when one reaches the Eddington limit for dusty gas, typically a few percent of the Eddington limit, then most of the material is swept away. This is shown here in this cartoon. At low Eddington ratio, we find that about 85% of the sky of the AGN is covered by gas and dust. And when one moves towards higher Eddington ratio, so with Eddington values of about 10 to the minus 1.5, the covering factor is much lower. And most of this Compton film material with column densities between 10 to the 22 to 10 to the 23 is actually swept away, and it possibly ends its life as some sort of polar wind. Something that is really interesting is that over the past decade or so, there has been a lot of evidence brought forward for the detection of elongated emission in the mid-infrared. And in particular, both with the VLTI and with the VLT, it's been observed that there is a lot of emission, in some cases even most of the emission in the infrared coming from the polar direction. And this is shown also here in this image. Those are visier photometric images of local AGN with scales of hundreds of parsecs, which found that actually this elongation goes in the same direction in most cases of the natural region. So what we could be seeing here in this extended emission is basically the dust that is swept away from radiation pressure. There has been some recent effort to look at how much of the extended emission one sees as a function of the Eddington ratio, which is shown by this plot here. On the y-axis, you have the fraction of extended flux over a result. On the x-axis, the Eddington ratio. And there's been, these authors reported a correlation between these two quantities, which would be consistent with the idea that as one moves towards higher Eddington ratio, more and more of the dust from the torus is brought towards the polar region by radiation pressure. Using BAS with Daniel Asmus, we have been looking recently at the properties of the mid-infrared spectral energy distribution of AGN, because the idea is that if like the structure of the torus is changing as a factor of the Eddington ratio, one would also expect to see a difference in the mid-infrared emission itself, besides seeing a different morphological difference as reported by the studies I mentioned earlier. What we are finding is that there seems to be a difference when one moves towards higher Eddington ratio. This plot shows the normalized SCD. So this is WISE photometry for about 500, 600 Swift-Platte AGN. On the x-axis, you have the different wavelength for these four bands. The left-hand panels, so this one and this one, are basically the whole sample. And on the right-hand side, we are showing the sample only of most luminous sources, just to make sure there is no additional effect due to different luminosity, since there could still be contamination in the infrared. And this is done for unobscured sources, which is the top panels, and obscured sources. And you can see that there is some difference here in the obscured range with the sources that accrete a higher Eddington ratio, showing typically a redder SCD that could be due to a stronger contribution of the cold dust that is found in the polar region due to these outflows. All this brought us to think that probably the unification model of AGN is not really a single one-dimensional scheme, but there is at least another dimension that should be considered, and that is the Eddington ratio. So that the probability of an AGN to be obscured is actually a function of at least these two quantities, theta and the Eddington ratio. So that when one looks at a source at higher Eddington ratios, the probability, regardless of the angle of observing a source as unobscured, is actually much higher than at lower Eddington ratio, just because the covering factor of the material is much smaller. So while the contrary happens at lower Eddington ratios. This is, of course, not the end of the story. In reality, it's much more complex, and in particular, it's been shown that luminous dusty quasars at higher redshift, they seem not to really care about this Eddington limit for dusty gas, and they are typically found in the region where one would expect no AGN. So this plot shows the column density, so how much gas one sees in the line of sight as a function of the Eddington ratio. And the points here are the Swift-Platte data that I was showing earlier in this one-dimensional picture, in which you have the fraction of obscured sources as a function of the Eddington limit. The color point here are from this paper by George Lansbury, also at Cambridge, in which he showed that these luminous dusty quasars, they are typically find at higher Eddington ratio than the effective Eddington limit. And this is true also considering newer versions of this effective Eddington limit. So something must be different for these sources. This could be either due to the fact that the obscuring material is located on larger scales, than the sphere of influence of the supermassive black hole, so that the only parameter that is affecting radiation pressure is actually the number of photons and therefore the luminosity, or there could just be a transient phase in which the source is basically starts to increase much more rapidly and is starting to create this outflow, but one can still observe for a short phase the source as having both high obscuration levels and high Eddington ratios before the source itself, the source becomes unobscured. One possibility is also that this is all related to the effect of mergers. It's been speculated and shown theoretically that when two or more galaxies interact, the tidal forces basically deplete the angular momentum of the gas, funneling it towards the inner kiloparsec. And all this gas and dust that is moved around during the merger could end up obscuring the accreting supermassive black hole, as shown in these simulations here, where you have the column density of the gas on the y-axis as a function of the time during the merger. So at early times, this is done for the two different galaxies. So the two lines, the purple and the blue line, are basically the two galaxies that are interacting. At the very early phases of the merger, so the first giga year, when the two galaxies are well separated, one can start to see periods in which the level of obscuration increases due to this funneling of material towards the center. But most of the absorption is actually seen when the two galaxies are found very close to each other, and typically on around 1.5 to 2 gigayears. And the maximum column density is actually reached when the two galaxies are coalescing, and one expects to see very high level of obscuration in this period. In order to test this, we recently looked at observation of 32 merging galaxies from the gold sample, which is a sample of infrared bright AGN, which span a very large range of merger stages. So there are sources like this one, in which you have two galaxies. They are well separated. You really don't see any sign of tidal tails. There are other sources like this one, where you clearly see the leftover of mergers. Others train wrecks like ARP220, and sources that are post-merger. So in order to study what happens to AGN during and after the merger, we selected all these galaxies. We divide them according to their merger stage, and then we looked at their obscuration properties. This is an infrared sample, so in principle, it's not affected by obscuration itself. The results of this work are shown in this plot here, where you have the cumulative distribution of the column density for different types of, for AGN in different types of galaxies. So the red dotted line here shows the Swift blood sample, which is mostly made of AGN in isolated galaxies. The dashed blue line is objects found in early mergers. So something like this, when the two galaxies are at distances larger than something like 10 kiloparsec. In some cases, you can see tidal tails, but they are not, they still have projected distances that are very high. And the orange line are the AGN which are found in the late stages of the mergers. And you can see that there is a very clear difference between the AGN in the late stages of mergers and the others, because in the final phases of the mergers, the AGN tend to be all heavily obscured, so with column densities above 10 to the 23. And this is typical. This is very different from what we saw for Swift blood AGN, for which only something like 40% of the AGN had similar levels of obscuration. This means that something is happening that is increasing the obscuration, and that mergers can also play a strong role in changing the obscuration properties of the accreting supermassive black hole. Going back to our idea of unification, this means that we need at least another dimension that is given by the merger stage to reconcile different classes of AGN, in particular obscured and non-obscured sources. So with the increasing merger stage, so with sources getting closer and closer, typically the levels of absorption increase strongly. Okay, now for the last part of my talk, I want to talk about another exception to unification schemes that are changing look AGN. Those are sources that transition from either being obscured to unobscured, or from showing only narrow lines to showing both broad and narrow lines, and the other way around. So those are sources that somehow defy this unification scheme because something else is at play in these objects. In particular, I will focus on what we call the optical changing look AGN, which are the objects in which no narrow line is observed, then all of a sudden something changes, in particular the accretion rate, and a broad line is a broad optical line or UV line is created. Here is an example of this changing look AGN. Obviously, here the difference cannot be the obscuration, because obscuration doesn't change on the time scales typically observed for this transition. So this example shown here shows in black the optical spectrum from 2005, and then 12 years later, so you can see a much broader line that was not observed in 2005. There has been a lot of discussion over the past several years on what the drivers of these changes might be. It's been argued that they could be related to state transitions, such as those observed in black hole binaries, with the source all of a sudden changing its state, so going from relatively inefficient to a Shapura-Sunyaev accretion disk, and in doing so, creating a large amount of extreme UV radiation, which then powers these broad lines and just increasing the ionization field. Another possibility is that they are related to disk instabilities that affect the broadline regions where they are produced. And finally, they might be related to some transient events, such as, for example, tidal disruption events. And this is something that it's been discussed, but it's been unclear whether it can really be the case. There are a few candidates for which this works quite well, and I'm going to discuss in detail one of them. That is the changing look AGN 1AS 1927. This is a source that was observed before as not having any broad line, so it showed us an optical spectrum with just some narrow lines. In the X-ray, it looked like normal AGN from a purely spectroscopical perspective, but it didn't show any obscuration, regardless of the fact that there was no broad line. Here, I'm showing you the optical and UV light curve of this object. We detected it, we started studying it after it was detected by the Assassin survey. It was found to show a very rapid increase in optical flux, after which we started our monitoring campaign. You can see that after this first period, which the event started in late 2017, there was a decline both in the optical shown here and in the UV as collected by Swift UVOT and shown here. And one interesting thing is that this decline follows a curve that is not too different from the T⁻⁵ that is commonly observed in TDs, although nowadays there are many sources that are classified as TDs and don't show any of this behavior. So this is hardly conclusive. This was published in a paper in 2019 by Benny Trachtenbrot. And here you can see the most interesting part in the optical UV, that is the change in the spectrum. The historical spectrum is showed here in the bottom. You can see that there was no broad line. And right after this increasing flux, we started our monitoring campaign, and we were able to witness the appearance of the broad lines. This happened about 3 months after the event. And then after a couple of years, 1.5 years after the beginning of the event, the broad lines disappeared. And this is also something that is kind of uncommon in this changing look AGN. So quite interesting. What this motivated us, of course, to start observing the source in the X-rays, and that's where we found the most, possibly the most interesting behavior. We started our campaign about 150 days after the event. Here you have the light curve, so the luminosity at 0.5 to 10 keV, as a function of the time. The blue points are the nicer observation. We had a large number of nicer observations since this source was so interesting, plus some joint XMM Newton new star and a few Swift XRT observations. Right after we started our observations, you can see that the flux of the sources decreased very strongly, went down to 10 to the 40, which is about 3 orders of magnitude lower than the historical luminosity, which is shown here in green. After this, there was a very rapid increase, with the source going up 4 orders of magnitude in about 100 days. And you can see also that the intraday variability is very high, typically a couple of orders of magnitudes within 10 hours. And as the source luminosity increased, the dispersion of this variability, the dispersion of the flux also decreased and reached some asymptotical values. And basically, it's been at this a few times 10 to the 44 for a while now. Spectroscopically, the source in the X-ray band looked like a normal AGN. This is the XMM Newton observation in 2011. You can see some power law components, some soft emission. This is some absorption, but overall it doesn't look very different from a typical AGN. Right after the event, however, this hard X-ray emission that is observed in all AGN completely disappeared, and the source became super soft. This is a shape that reminds of tidal disruption events, which are dominated by this black body component or X-ray binaries in the soft state. And this also means that this X-ray corona, which produces all these photons in the hard X-ray band, completely disappeared, or almost completely disappeared. Here you can see still some flux left. So something really tragic, dramatic happened in this source that destroyed these innermost regions where the X-ray corona is found. At later time, when the source was fainter, it was even softer. There was no hard X-ray emission observed. In August 2018, the flux increased. The source was still very soft, still very little or no power law emission. And then in 2019, the source became much brighter, and some power law component is observed. The same in August when it was even brighter, but this emission is much softer than the typical shape observed in AGN and what was also observed historically for this source. This means that something dramatic really happened in the innermost regions of the accretion flow, and then somehow they are being refilled as the time goes on. A possible explanation is that this is related to transient events such as a tidal disruption event. There have been some simulations recently showing what happens when an accretion disk interacts with the tidal debris created by tidal disruption events. So I'm going to show you now the results of these simulations. Here you have the accretion disk. The color shows the density observed pole-on. And I'm going to start the simulation. Now you're going to see what happens when the tidal debris hit the disk. This basically depletes the shocks of this interaction, deplete the angular momentum of the gas, which practically increases the accretion rate because the material just starts free falling, and empties the innermost regions of the disk. So basically, the strong accretion rates between in the innermost regions, this makes all this material disappear, while the outermost material, which has still a lower accretion rate, only later starts to refill this gap. And this is what might have happened to this particular source. Here is a cartoon that summarized a possible explanation for this event. So this is the source as was observed before the optical UV event, with the supermassive black hole at the center, the accretion disk. This is the magnetic field powering the X-ray corona. As the debris hit the disk, the accretion rate of the innermost region increased, so that the source started to eat more and more of this inner disk, which led to basically an empty, depleted innermost region. in which also the magnetic field lines, which are associated to the accretion flow, disappeared or became very faint, so that the X-ray emission also became very faint from this power, while the material was still dominated, the emission was still dominated by this soft component. As the innermost regions of the disk are refilled, then the disk is recreated as well as the X-ray corona, so that a faint magnetic field is basically powering faint, weaker corona with a much softer emission. This is, we are still continuing with our monitoring campaign of this object with XMM Newton, New Star, as well as NICER. The source is still, as I was mentioning, at a very high flux level. We are curious to see what's going to happen later, but it's even more exciting to think how many of these incredible transients are going to be picked up by new facilities such as Rosita, which is doing scans of the X-ray sky, or in the future by the Einstein probe. And we might just be looking at the tip of the iceberg of creating supermassive black holes that have actually a much more dynamic and exciting life than we believed before. Okay, I'm going to leave you here with my summary. I showed you that most of the AGN in the local universe are obscured. This obscuration at the level of about 70% in nearby sources is regulated by radiation pressure. And in particular, the calming factor of the obscuring material changes very much depending on whether the source is above or below the Eddington limit for dusty gas. Another way to affect obscuration and to give rise to heavily obscured sources are mergers. Mergers are extremely efficient in creating heavily obscured AGN. And another interesting aspect of the unification scheme related to these exceptions that I mentioned in the last part of the talk, the changing look AGN could be caused by extremely transient events such as tidal disruption events. And it is a field that I think it's going to become extremely important in the coming decade. And I'll stop here and take any questions. Thanks.